Welcome to week 2, session 1, that's 21 of the summer school on large language models. All of the videos from the first week are online now at the link that you can find on in the WordPress document, or write to me and I'll send you the link. Our speaker today, and there's two changes, well, one swap in the program. Danilo Bezdok will be speaking today at the time that would have been Tom Griffiths, because Tom Griffiths got serious COVID, and he's transferred optimistically to Friday, the last session where Danilo had been. So this will be Alessandro Lenci, and the next will be Danilo Bezdok. I will read his bio when it's his turn. The talk by Alessandro is the missing links. Well, you see it on your screen. I won't say that. Alessandro is professor of linguistics and director of the computational linguistics laboratory, CoLing, University of Pisa. His main research interests are computational linguistics, natural language processing, semantics, and cognitive science. And with that, I hand it over to Alessandro. Welcome.
Thanks a lot, Stephen, for this introduction, and thanks a lot also for inviting me to this fantastic summer school. It's really an honor and a pleasure to talk to all of you. I will start with just something I did yesterday on using the last version of ChatGPT, and I asked the model a question like this: a new type of robot called Blimp as a kind of artificial arm as one of its parts, the arm as a hook, and then I asked the model, is the hook a part of the Blimp? And this is actually the answer that I got from the system, which is not only correct, so it infers that yes, the hook is a part of the Blimp, but is also very analytical, logical explanation of its application of the transitive property of part of relations, and this also concern an invented entity like a Blimp, and in a way, it's hard to imagine that this is not really something close to human natural language understanding. And although this is what we experience every time we usually use models like ChatGPT, part of the main argument of my talk today is that there is still what I will call a semantic gap in large language models, which we can define by saying that the large language models still lack substantial aspects of human semantic competence. I want to stress the word still. So I'm not saying that these models will never be able to fill this gap. I'm saying that nowadays, and perhaps the model as they are, still have some limits in specific aspects of human semantic competence. And part of, the talk today will be exactly to try to investigate where this semantic gap lies, which aspects are concerned, and also possibly imagining which kind of steps are necessary in order to fill it. Part of my arguments are also very sympathetic with the position that has been advanced by Kyle, Mawald, and others in their papers, in which they distinguish between formal linguistic competence of large language models, and which is knowledge of linguistic rules and patterns, ability of producing linguistic expressions that are formally undistinguishable from human ones, and what they call functional competence, namely a real ability to understand and use a language as we do. And part of the arguments by Kyle and others is exactly that large language models have an almost human-like formal competence, but still, fall short of a lot of aspects of functional competence. First of all, I would like to remind to start from the basics, or at least to start from the past, in the sense that we should never forget that what large language models actually are and where they come from. Okay, so basically they are just let's say the last generation of what we used to call distributional semantic models, namely models that really extract knowledge from textual data, and they use to, let's say, to represent meanings, aspects of the meaning of linguistic expressions in vectors, embeddings that are supposed to encode the statistical distribution of words in linguistic context. And in fact, I mean, if we look at these pictures, which we could, I mean, it's called the trees of large language models, we can see that the large amounts and numbers of models that have appeared in all these years are just derived by, have their roots in exactly models that were very popular until a few years ago, like word2vec, fast text, and glove, and so on. So on the one hand, there is something which is old, in the sense that it's something really that we already have seen for many years, and on the other hand, there is also something genuinely new in these models. So first of all, I mean, like the previous generations of what we used to call predict distribution semantics models, like exactly word2vec. The idea is that large language model can acquire knowledge from text corpora only by training with a self-supervised string prediction task. So they basically, acquire information about the meaning of words by predicting which other words they occur with in context. And this is exactly basically the same learning objective of GPT, like used to be, for instance, for word2vec. On the other hand, there is also something genuinely new in these models that we all know, which is also first of all, we know that they are much more complex and deeper, narrow architectures with respect to the previous generation distributional semantic models. They are trained on much larger amount of data. That's another things that we need to take into consideration. And also, and this is also really the most surprising aspects in a way, the array of knowledge that they are acquired from data by this model, it's much larger than the previous generation of distributional models. So traditional distribution semantics models like word2vec, for instance, were essentially conceived as models of the lexicon. So they were supposed to acquire knowledge about lexical types. On the other hand, we know that large language models encode really non-trivial aspects of syntactic structures, as we also seen last week, for instance, in various talks. Important aspects of sentence and discourse meaning, word knowledge, but also pragmatic dimensions, and all of these things put together is result in that surprising behavior that we have seen in the first slide, when they are asked to solve also semantic questions about part of relations. Now, the problem is exactly this. So if we remind us that basically large language models are just the distributional devices, so the devices that learn what they know entirely through distributional learning from contextual, from linguistic information, the question is whether distributional learning really suffices in filling the semantic gap. So is distributional learning enough in order to acquire human-like semantic competence? And of course, this in turn this question can be split into two further questions, namely, okay, but when we speak about the human semantic competence, what does it consist of? I mean, what is semantic competence? And then, of course, which aspects of this semantic competence can be learned from distributional data? So there is a widespread claim an argument that basically the semantic, that indeed the large language model have a semantic gap, but this semantic gap would mainly reside in the lack of referential grounding in the external world. So this is exactly a picture taken from the paper by Bender and Kohler in 2020, where they proposed this so-called octopus argument, which is a kind of revisitation and renewal Chinese room argument by John Searle, which is basically, well, any kind of entity which is just trained on learning distributional statistics is not able to acquire only by distributional statistics aspects that refer to the world. Of course, this is an aspect that mainly and essentially concern text-only large language models. So language models are essentially trained on text only. Well, we know that there are other type of large language models, multimodal ones, like also the last generation of GPT, like GPT-4, GPT-4o, and others, what indeed seem to have also some kind of ability to refer and to link language to the world. This is just another try I did yesterday with a very popular picture that is we usually taken in Pisa, where there are some tourists that are trying to they take a picture in which it seems that they hold the Leaning Tower, but this is just an effect of the perspective. And the description that is given by the model, it's in a way quite surprising, because it says that the image shows a person standing in front of the Leaning Tower, appearing to hold the tower with one hand due to the perspective of the photograph. And then there are a lot of information that concern really reference. So the fact that there is a person, this person wears a straw hat and a black shirt and carries a red bag and so on. So it's also appears that in a way, it's true, text-only models cannot grasp referential aspects of the world, but these models can be made multimodal and also integrated with information concerning not only extracted not only from language, but also from other modalities like images. So I think that, and this is essentially the main argument of my talk, is the fact that, yes, it's true. I mean, surely grounding and reference to the world is an important limit of many aspects of large language models, especially the ones only trained on text. But there are also other aspects the semantic gaps concerns other aspects of their semantic competence. And for this, I will rely on a distinction which was advanced some years ago by an Italian philosopher of language, Diego Marconi, who distinguished between inferential and referential semantic competence. So Marconi talks about referential competence as the ability to map lexical items onto the word. So basically, which is exactly what we have seen in action when the model was able, for instance, to understand that there was a woman with a red bag in the picture, or when we, for instance, we say aardvark and we are able to point to the specific animal that the name aardvark refers to. But besides the referential competence, there is also another crucial aspect of the human semantic knowledge, which is what Marconi calls inferential competence, which is the ability to manage a connection among words, underline some performance as semantic inference, paraphrase, finding a synonym, and so forth. And what is inferential competence? Inferential competence is, for instance, knowledge that an aardvark is a mammal, that an aardvark has legs, and all this type of knowledge information, which is also relevant in order to draw inferences about aardvark, independently of our ability to refer to that actual animal in the world. Well, basically, There is a common argument on large language model and their understanding capability that actually, let's say, inferential competence is in principle not a problem for these models, in the sense that the idea is the fact that actually those aspects of meaning that the large language model would acquire would exactly be those aspects of meaning that concern inferential semantic competence. For instance, Piantadosi and Hill in 2022, but also similar position was taken by Lee Public in more recent papers. They actually claim that the meaning that the large language models acquire from text corresponds to what they call the role that concepts play in some theory, in some greater mental theory, okay? And they actually link their position, their argument, to the so-called conceptual role theory or theory of concepts, which was argued for by Gilbert Harman in 1982. Namely, the fact that the concepts are a representation whose content is determined by the relations they have with other concepts, as specified by some kind of mental theory. In a way, this part of information here, so the fact that Harvard is a mama, Harvard has legs, are just bits of this theory, of our theory about, for instance, hard work, that is made also of specific relations that this concept has with other type of concepts, like, for instance, mammal, legs, and so on. So the idea is that this is exactly the information that large language models acquire from text. So they represent concepts with a role in some theory. So they are able to acquire from text, let's say, a theory of concepts, or let's say concepts in the sense of a kind of theory that specify their relations that connect with other concepts and so on. Given this assumption that this is exactly the type of meaning representation that the large language model acquire from text through distributional learning, the conclusion that we can draw is the fact, well, since conceptual role theory, or let's say this type of knowledge representation is exactly what support inferential semantics, large language models do acquire inferential semantics from distributional statistics. Moreover, there is also a further argument, which is taken by various authors, that actually even text-only models can also fill the referential semantic gap, since there is the possibility of mapping. So a mapping exists between, let's say, the semantic space, the distributional semantic space acquired by these models onto the perceptual and physical spaces. And since this map exists and it's possible to be, we can learn this mapping, even a model that acquires only information from text is able in a way to acquire some form of referential semantics exactly because of this kind of alignment between language and the perceptual spaces and the physical spaces. And this is basically, I think, a kind of revisitation, or let's say the different, I mean, it's very similar to what Max Lowers also called the symbol interdependency hypothesis, namely that since the sensory motor information is encoded in language, through language statistics, we can also acquire the sensory motor information about the external world. Well, basically, so what I will try to investigate and I will present you in this talk is exactly something that is related to the question whether distributional learning suffices to let a large language model at least acquire some true inferential semantic competence. And so basically, the questions I want to ask is whether large language models do acquire a true conceptual theory. So is it correct to understand the distributional semantic space in terms of a conceptual theory in the sense of this sense here, so in the sense of Harman, in the sense of the theory of concepts. And so again, what aspects of inferential semantics can or cannot be learned from distributional data alone? Well, on the one hand, if we go back to the first slide of my talk, and we can see this very beautiful logical argument that is presented and this inference, it seems that all these questions have already an answer. So yes, these models can do all these things because, I mean, if they are able to carry out that type of inference, we should at least assume that they have indeed inferential semantics, that they indeed have that are able, they possess kind of conceptual theories of entities that they have learned from distributional data alone. But I think that if we investigate these issues more closely and more, let's say, systematically, well, I think that a gap still exists. So again, these models do acquire a lot of information from text, but whether these informations, the knowledge they extract from text can genuinely be described as a true conceptual theory is questionable. Okay, first of all, I will present you a couple of ongoing work that I'm doing with some of my from collaborators in my group, and one of this research concerns exactly meronymy. So the part-whole relation that we have seen in the example at the beginning of this talk, and as we said, I mean, the part-whole relation is an important aspect of inferential competence. And let's say, if we have a theory of an entity, we also know which are their parts, which things are not their parts, and so on. And one key property of meronymy is asymmetry. So understand, meronymy is an asymmetric relation. So if A is a part of B, necessarily B is not a part of A. And so the question is whether the language models knows the parts of objects, and especially knows that the part-whole relation is truly symmetric. To investigate this issue, we have collected some meronyms from various sources. We use the McRae norms, which are human-generated features for a number of concepts, and so we extracted all the features that were specifically labeled as meronyms. And we also extracted the part-of relations from ConceptNet, which is another handmade conceptual network based on also human judgments. In the whole, we extracted 900, almost 1,000 part-whole pairs from McRae, and again another approximately 1,000 part-whole pairs from ConceptNet. And we wanted to test whether different type of language models, how these language models deal with the meronymy information. And we did experiments with 3 models. The first one is Llama 2 without instruction tuning. Namely, this is really a foundational model. This means that Llama 2 only acquires information from the prediction learning objective that we have seen before. So it's a basic distributional model. Then we use an instruction tuned version of Llama 2, which is basically a language model that has been instruction tuned and so on, is specialized for chat. And then we also use the GPT-4 model that also has been tuned by, which is way bigger than the other models, and it has also been tuned with reinforcement learning from human feedback. We tested with these models on 2 tasks using prompting. And we prompted these models on a question task about meronymy and on a statement task, which is basically target exactly the same type of informations, but in a different way, also because we know that prompting can be subjected to different type of, to variations, also in the way the task is formulated. So, and for instance, in the questions task, the prompt was your task is to answer the following question. So you must answer strictly with yes or no. The question, is the wheel a part of the car? While in the statement task, we presented the part of relation is a statement, the wheel is a part of the car, and the model has to answer true or false in the task. Now, the important thing is that we tested each meronymy pair, X and Y, in a direct and a swap test. What is the difference? Well, the difference is that in the direct test, the sentence was presented in this way. The X is a part of the Y, and the correct answer was true. While in the swap test, we presented the sentence in the reverse order, and we said that the Y is a part of the X, and in this case, the correct answer was false. Okay, and we defined what we called a meronymy knowledge criterion. What I mean by this, that we can assume that the model knows that the pair XY is an instance of meronymy if only if the model correctly solves the direct and the swap test for the pair XY. So basically, a model knows that a wheel is a part of a car only if I say it's true to the statement the wheel is a part of the car, and false to the statement that the car is a part of the wheel as in the swap direction. Now, what we found is the fact that these are actually the results that we got for the models. And this is the global accuracy of the models. And on the left, it's the question task. In the right, the statement task. And the blue is the ConceptNet data set, and the yellow one is the McRae data set. And as you can see here, if we start with let's say, foundation models, so just the one trained with distributional learning, performance is really, really bad, in the sense that there is just a 27% of accuracy, for instance, on ConceptNet in the question task, which is approximately the 1% in the statement task. And in general, you can see that the statement task is much harder than for the models than the question task. An improvement exists in the instruction-tuned one. So Llama, you can see it performs better. And of course, I mean, the best model is GPT-4, but notice that in the ConceptNet, even the best models, the best model reaches, for instance, on ConceptNet, just 69% of accuracy on the question task, and 66% of accuracy in the statement task. And in these cases, we have also to remind that. To remember that GPT-4 is not a foundation model, so it has the statistics extracted from text plus a large amount also of refinement due to the human reinforcement learning. And even more, GPT-4 is not only trained only on text, but is also multimodal. So it has been trained also on images. So in this sense, there is also information coming from external to language. And despite the dimension, there is still quite a big gap in the ability to properly recognize meronymy and the directionality of meronymy, the symmetry of meronymy. Then we also wanted to understand the fact that we also wanted to explore the fact that maybe this performance might be due to the fact that these models do not know some of the meronyms. So although it might be unlikely given the amount of text they've been trained on, that's still a possibility. So basically, we know that all these models are models that are especially optimized for generation. So they are all generative models, all decoder-only large language models. So they are optimized for text generation. And so we also design a part generation task. So in this case, the task of the model was to generate part of objects. Okay, and we gave the models the holonyms, so the concepts, the target holonyms that we use in the previous experiments. We asked the model to generate parts. And these are the statistics. So you see that we only did this with the two better models, so two best models, so GPT-4 and the Llama Instruct, because the non-instruct model was, the performance was, and since this model is not optimized for chatting in a way that we expect it to have, in any case, a very noisy result. So you can see here that these models generate a lot of parts, a lot of meronyms. And we also carried out the manual validations of all these meronyms. And you can see that we validated all the meronyms generated by Llama, and we got an accuracy of almost 93%. So all 93% of the parts were correctly generated, were correct parts. And also we did a sample, we took also a random sample of 300 holonyms, and we manually validated all the parts generated for these 3 holonyms. And again, for GPT-4, the accuracy is very high, between around 97.5% of accuracy. So this means that these models generate a lot of parts, know a lot of parts of these entities. And so we decide to carry out another experiment, which is exactly to say, okay, let's try to test these models on the same task that we've seen before. So the question and the statement task to understand for meronymy identification by using as data the parts that they were generated by these models. So basically, the aim of this experiment was to answer questions like, but do these models know that the parts that they generated are actually parts and satisfy the asymmetric property of meronymy and the meronymy knowledge criterion? And this is what we got. And we can see that, again, for Llama, only approximately 45% of all the parts, so of all the meronyms that were that were generated by the model, were also recognized correctly by the model itself as parts. And again, GPT-4 has a much higher performance, but notice that, for instance, in the question statements, it reached only 81%, which goes down to 74% in the statement task. So this means that even for GPT-4, approximately 1/4 of the parts that were generated by these models were actually not recognized by these models as being part, didn't satisfy the meronymy knowledge criterion that I showed you before. So basically, the conclusion is that the large language models do not always know that the parts they generate are parts, or they do not know that these parts have the properties of meronyms. And this is an instance of what has been called the generative AI paradox, namely the fact that in many cases these models perform much better in generation rather than in understanding. So in some sense, there is a mismatch between what they generate and what they truly understand from languages. And this case of meronymy seems exactly to be one instance, one example of this problem. As a last task on meronymy, we also try to design a meronymy logic test. Basically, the idea was to give the model sentence pair that differ for their truth conditions. You can see, for instance, in some cases, one was true and the other was false. like the tail is a part of the dog, true, the dog is a part of the tail, false. In other case, both sentences are true, the tail is a part of the dog, the arm is a part of the body. In the fourth case, in the third case, two sentences are false. And then the fourth case is we have the reverse of the first case. So the dog is a part of the tail is false, and then the tail is a part of the dog is true. And basically, the idea was exactly to test whether the model was able to assign the right truth conditions pairs to the sentences. Again, to understand that this is true and the other is false, or in this case, to say that this is false and the other one is true. And we did this test in one version, which is like this, with this type of prompt. And in a second version of this prompt, we also give the model a rule to be applied. So we specifically ask the model to apply the rule that concerns the asymmetry of meronymy. So if A is a part of B, then B is not a part, then B is not a part of A. And these are the results. And we carried out we performed these models, this experiment only on GPT-4, which, as we have seen, is just the best model. Now, interestingly, notice that the models, without the rule, they have quite very high performance, 92% in recognizing, for instance, that correctly recognize the true-false pair. But interestingly, this performance changes if the same sentences are presented in the reverse order. So while in these cases, so when we have these cases in which the two sentences appear in the order true, false, the performance is higher, but drops when the order is reversed. Interestingly, by providing the rule that should be applied by the model in performing this task, the performance of the model drops and is actually, and so it makes the model, it provides, I mean, it gives confusion, so it makes the model be confounded rather than help the model even more. So, and now in a second experiment, in a second, let's say, case study, we have been investigating, this is really something that is still to be largely completed, so just a really preliminary result. We investigated the causal relation. Why causal relations? Because again, cause-effect connections are an important ingredient of theories. Okay, so knowing a theory of events means also being understanding whether these models, between two events, there is a causal relations or not. Moreover, causal relations is strictly related with temporal precedence because the cause precedes the effects, but causality is not merely temporal precedence. So the first causal relations cannot be reduced only to temporal precedence. So what we built is a data set of sentence pairs that contains implicit causal relations. Namely, what I mean by this, these sentences contain event pairs which are related by causal relations because of our, let's say, knowledge of the world. So let's say inferential knowledge or general knowledge, but but they don't. There is no explicit connective link in the two sentences. And we had 200 sentences in which there is an implicit causal relations, and 200 sentences connected by an implicit temporal precedence relation, and 200 sentences that contain events that are not linked neither by causal nor by temporal relations. And all these sentences were classified by 5 expert annotators in order to identify whether the two events were causally related, temporally related, or neither of them. I will focus only on the two cases of causal and temporal sentences. So we decided to understand whether semantic large language model were able to identify the correct relation and also the direction of these relations linking the two events by, let's say, understanding or by connecting. Sorry. There was an airplane passing by. By understanding whether which was the connective that explicitly, the correct connective corresponds to a certain relation. So this means that starting from a certain event pair, we design sentences that linked the two original sentences by a certain connective corresponding to causal relation, where the cause precedes the effect, like in the first cases, a causal relations in which the cause follows the effect, and again the temporal relations in which the preceding event precedes the following event, and the reverse situation in the four cases. So in these cases, A, B, we could consider a kind of iconic order in which the cause and the preceding event appears before the effect of the following event, and BA, the anti-iconic order in which the cause and the preceding event appears after the effect of the following event. In these cases, each relation and order was explicitly associated with a connective. So what we did, we took four models, four large language model, all of the instruction-tuned family, so Bloom, Falcon, Llama, and Mistral. And basically what we exploit, instead of using a prompting experiments, like in the case of meronymy, we actually measure the perplexity of the sentence with the models. So we use the models in, let's say, in their original and more direct way of providing the probability and so the perplexity of a certain sequence of elements given a context. And basically, we see that we designed for each event pairs four possible items, in which one the connective was the correct one given the relation and given the direction of the relation. So Luke cut his hair because Luke's hairs were too long, and that's the correct one. And three other distractors in which we have the same events in the same sentence, in the same order, but with connectives that were not consistent with the relations expressed by the two events. And so basically, the idea is the fact that a semantic relation and order is correctly identified if the model assigns a lower perplexity to the sentence containing the right connective. So in these cases, we expect that the perplexity assigned to them by the model to the first sentence is lower than the perplexity assigned to the other sentences. And in these cases, if so, we score the hit and we measure the accuracy. Okay, this is the global accuracies of the models. And we see that in all the models, the general accuracy is not, I mean, is way over the baseline, but it's also is actually not beyond the 65% globally. But it's interesting to see just also where the models goes wrong. What is the confusion? What is the problems that these models? And I will show you just an example from the best model that is the Mistral one. In these cases, you can see that, okay, in the diagonal, we find the correctly understood relations. We see that, for instance, even for the causality relations that are in the direction AB, so the cause precedes the effect, we have 78% of accuracy, but 12% of cases are confounded with the reverse order. Interestingly, the best results we are obtained when the effect is presented after when the cause is presented after the effect. Notice that in any cases, we found that in the case of temporal precedence, we found a significant number of cases of temporal clauses which are interpreted as being causal related. So this means that the model is very good identifying causes when there are causes, but many cases of temporal, simple temporal precedence are confounded to be caused. And also there is quite a significant number of cases in which the model also confound the order of the events, which is again a piece of evidence that these models have, I mean, strive to cope and to deal with the clear distinction between causal semantic relations versus temporal precedence relation, and also with concerning the order in which these elements, these relations are applied. So I'm coming to the to some conclusions about from the evidence I also showed you. So again, distributional semantics model, we started from the idea that large language models are actually just distributional semantics models, or just a derivation of the same approach. Truly, they identify highly sophisticated distributional associations between linguistic expressions, but I think that they still lack a semantic spaces organized in terms of through theories. And the fact that some of the evidence that I show you today are really consistent with other works that have been carried out recently, other results that appear recently, in which exactly point towards the same problem. So these models are really not able to recognize through theories in the sense of concepts. Especially if we understand, if we remind what is a theory. So a theory is not just association. So a theory is a structured network of entities and events that are linked by relations that specify their functional role in a system. So understanding what a theory is means understanding that a cause, something X cause Y, it's not the same as X precedes Y, or A is a part of B, is not the same as B is a part of A, and so on. So basically, we can see that the distributional semantic space of CAR, probably even in the more complex model, resembles something like on the left of this figure. While when we think about a theory, or we talk about a theory, we should think about something closer to the one in the right, in which we really have knowledge about CARMs in terms of associations with other concepts, which also make in which the different role and the different functions of the different entities in the overall theory is taken into account and distinguished. Interestingly, I think that another small piece of evidence, I understand this is more anecdotal, but I think it's a nice it's a nice aspect. It could be a nice aspect to reflect on. Is exactly the fact that even the largest models encode a lot of features, a lot of aspects, but these models, the aspects are, especially in many cases, are described as being conceptuals and so on, but actually they are not really semantic feature. Okay, what is this? Perhaps you have read the recent paper appeared by people from Anthropic that was entitled "Mapping the Mind of a Large Language Model," in which basically they applied let's say, sparse encoding methods in order to identify the features that are encoded by large language models, and also to identify which features are most activated by words that are given to input to a large language model. Okay, in this paper, in this work by the people in Anthropic, they also identify what they call a part of member of a feature, which is exactly this one. So the feature, this is the number of the feature. And if you go to their site, you can visualize what are the words that this feature activates most. And correctly, we see that, for instance, is the word part of that activates most this type of feature. But notice that in many instances of these uses of part of, this is not a real meronymic relation. Notice we have something like, it was at this point they realized that it was part of the problem and not part of the solution. Okay, they are all part of this great big conspiracy. They are part of me. So what does it mean? It means that this so-called alleged semantic feature, it's not really semantic features. It's the pattern part of that these models learn to encode. The problem is that the pattern part of is, of course, a way to express meronymy, but is also a linguistic way to express other type of relations, or is also used not to express really part of relations in the strict sense of the term, right? So in these cases, you see, again, what we call semantic features are actually, in some cases, really very frequent patterns or surface patterns that these models are learned to encode. But I think that there is still a distinction between this pattern and this so-called feature and truly semantic feature and truly semantic dimensions that these models, in some cases, might not really still be able to encode. And I would like also in this talk in this presentation I've talked a lot about semantic relations, and see some cases in which even the largest language models have some problems in identifying this type of semantic relation. Now, we should not forget that the identification of semantic relation was also a pain in the neck of good old distributional semantics, in the sense that classical distributional semantics models have always had problems in discriminating between different semantic relations. This was just a case of, for instance, the neighbors of words like car, good, and buy, and we taken from word to vec, and we can see that among the closest neighbors of car, we can find a cohyponym, but also an hypernym. Good as its hypernym, as its nearest neighbor, almost synonym like excellent, but also an antonym, and so on. And the same we have by and the antonym cell, and so on. And in fact, a lot of work has been devoted in the distributional semantics in order, for instance, to identify semantic relations in distributional spaces. And for instance, one famous hypothesis that took a lot of attention in distributional semantics was the idea that semantic representations were or might also be encoded really in the linear, were linearly represented in the semantic spaces. This was the so-called linear representation hypothesis that was advanced by Tomasz Mikolov in 2013. And actually, it has been also has received new attentions on large language model recently in some papers. So basically, the idea that well, if we can see concepts like man and woman and king and queen as dots, as points in a vector spaces, actually the relationship that exists between man and woman, what we could call the gender relation, because woman is a feminine of man, is actually encoded by this linear vector, by this vector here, by this direction in the space. Okay, so this direction in the vector space encode the semantic relation of gender, which makes possible to say, and that was the hypothesis, that, for instance, the relationship that connects man and to woman is the same as the relationship that connects king to queen. And so basically, even if these elements are in different areas of the semantic space, the distance and the vector linking these pairs of elements are the same, and this vector would represent the gender relation. Now, this was a very interesting hypothesis and very powerful hypothesis about the structure of the vector space. But unfortunately, has been, although it received also a lot of attention, has also been received a lot of empirical falsification, in the sense that the relationships are not so neatly encoded in the vector spaces. Just to make an example, this linear representation hypothesis was exactly used and tested in analogical test, analogy resolution test. Interestingly, these are just accuracy in the test, where this analogy works pretty well, not perfectly, are in analogies concerning morphology. So, for instance, walk is to walk like sing is to sing, or and so on. Or walk is to walking like read is to reading. So the past progressive and so on. But when we took it into account, when you consider data sets, they encode a lot of semantic relations like hypernymy, meronymy, and so on. The performance of these models on this analogy task drops significantly. What
Alessandro, I'm afraid I have to interrupt. It's almost an hour now, and if you want some discussion, I think...
Yes, I'm just closing. Okay. So, just to close by, so the idea is the fact that large language models owe their behavioral success to the existence of strong correlations between word co-occurrence statistic and semantic relations. But despite this correlation, there is the semantic gap I've talked about derives from the lack of a perfect isomorphism between distributional statistics and conceptual and logical properties. And so basically, of course, the success of these models really depends on the fact that we have a close overlap between distributional spaces, inferential space, or the physical and perceptual spaces. But this overlap is not perfect, and it's exactly this type of let's say, the difference and the discrepancy between these different spaces that generate the semantic gap. So basically, the idea is the fact that the reason of the semantic gap really lies in the very type of knowledge that they extract from linguistic data. And so the fact that they actually do not extract really structured theories that might support an authentic inferential competence in the world. What are the solutions? I think that one solution is exactly that we can focus on methods that can leverage information acquired from statistical data, but can also learn to represent it as a truly knowledge structures. Possibilities will be that we can, for instance, enrich the prediction learning objective with semantic constraints to obtain a more refined semantic space. This is what actually a lot of research that was investigating distributional semantics models, which was called retrofitting, namely the idea that we could try to refine the learning objective of neural networks in order to learn specific semantic relations. Or, for instance, also try to make these models learn semantic relations in theory directly from grounded data rather than from scratch from large amount of text only. Okay, thank you and sorry for being late.
Thank you very much, Alessandro. And now your discussant, Friedemann Pulvermüller from the Freie Universität Berlin, will discuss not the cartography of the mind, but the cartography of the brain, I think. Go ahead, Friedemann.
Thank you very much. Thank you, Stephen, for the introduction, and thank you, Alessandro, for your fantastic talk. I will make a few comments, indeed touching upon the brain, but also let me just start with a more general approach, and I apologize in advance in case Alessandro, you sent me kindly your slides. I may have a citation here, which was on one of the slides I saw, but which was not in the presentation anymore. So in this case, please correct me and okay. So you made a very important point. GPT and other large language models cannot do some things about semantics. They are missing something. You speak about the semantic gap. This may be related, as you mentioned, by the fact that they are missing symbolic representations. Or in your words, also, they are missing true knowledge structures, real semantics in a sense, and in particular, inference schemes, and some of them easily formulated in terms of predication, are missing. So if we say rabbits have ears, and ears do not have rabbits, this is a relationship everybody knows, every human, but obviously, as you very importantly showed, ChatGPT is not bad at that, but there's room for improvement. Likewise, with inference schemes of the sort that if you of a more complex type. You also touched upon, but only very peripherally, on grounding in the world as something that could be a factor. But if I understood you correctly, then, and please again correct me if I'm wrong, my impression was you would suggest that adding this information about grounding might not help so much. Or are you, or is this right?
Do you want me to answer now? I would say no, this is not fully correct in the sense that I'm not saying that it's not adding much. I'm saying that on top of lacking grounding informations, there is also a lot of informations that is really cannot be recorded by this statistics alone, which concerns, let's say, more inferential schema. I actually believe that probably one of the problems of this model is that they could learn things like, for instance, part of relations by being exposed to grounded data. No, right. Yeah. For instance, so in that sense, I'm not saying that grounding is not essential. I'm saying that the reference problem is not the only problem that these models have. And if they are fed with images or with multimodal data, I think that a lot of problems come from the fact that they lack some inferential pattern. And also, let me add one thing. When I say that they lack inferential pattern, I'm not aiming for including symbolic representation in them, right? So I'm not arguing for the fact that the way to go is towards having symbolic structures. Let's say that they lack some aspects that, on the other hand, the symbolic models, of course, are able to deal with quite neatly, which are some inferences. But okay, so
yeah, thank you for the clarification. Let me just continue. And my one point I wanted to make is that if we look at standard semantic theories, they also you may also bring up against those that they do not include true knowledge structures in the sense of something that would allow inferential schemes. It's also, if you look at, for example, the Collins-Loftus model if we replace here the concepts by words and look at the co-occurrence probabilities in recent distributional models, there's just the correlation structure is mapped, but not these logical inference schemes. Likewise, if we look at semantic feature models, they also are composed of a particular representation is described in terms of a set of features and feature values, and those would also not necessarily be easy to translate into inference schemes. So, if we we may now say that these semantic models are in a sense if they come with features, and these features and we restrict consideration to those that have semantic grounding in the world, then and clear criteria for what the feature corresponds to in the world. We have a pathway from this type of model to a grounding approach. And my question would be whether indeed semantic representations are similar between these different types of models, or whether we could expect that by complementing distributional semantic models with grounding, we might improve the semantic representations already. And finally, I will make a few brief comment how this might indeed lead to something like basic inference schemes. This is a citation which I found on your previous slide, and there you say that that we actually would hope that there is a degree of correspondence between or overlap between the semantic information coming from distributional statistics and from the world. And so ideally they would provide the same information. Some people have claimed that, others but one might indeed object and say, is this indeed so? Would word-to-word correlations? So the question, how frequently, how well do words co-occur in texts, and would world-word correlations? How good is the consistency between the occurrence of a word and a certain pattern in the world, in the environment, in the grounding pattern? How would they relate to each other? Would they be indeed congruent, or only similar, or a little bit overlapping? And of course, everybody knows that we can convert these distributional semantics into semantic vectors and measure, for example, the similarity between the semantic similarity of two words in this particular framework, in the distributional semantic framework. We can also do the same thing in a grounding perspective, for example, by using features, grounded features, and build huge vector spaces with those, and also likewise measure angles between or Euclidean distances between the conceptual representations. And now the question might be whether these vectors are, in a sense, the distributional and the grounding ones are the same indeed as hoped, or rather not so much. And one way of assessing and visualizing these similarity spaces is called a method called representational similarity analysis. This got famous in the brain research domain, but it can also be applied to looking at cognitive and semantic measures and compare those. And one could, for example, then use one particular distributional semantic approach and compare it with a grounding experiential semantic approach. This is the result here we have 100 words or so divided in 6 categories: related words, animals, tool words, and so on and so forth. And so each word category has, I think, 16 or so items, and you can see the matrix would show you the similarity of a given word with other words from the same category, subcategory, from a larger category. Here action words, and here at the lower right object words. And then of course the diagonal is here the self-similarity, which is of course always very high. Therefore, we don't look at it. And then we see, what we can see here is that the degree of dissimilarity is rather low, sometimes for the individual categories, especially here. And sometimes there's a huge difference, a great dissimilarity here in red and yellow between the action word and object word categories, for example. Now, the interesting thing is, if we look at distributional models and experiential models, they produce very different patterns. And the correlation between those two is not overwhelming. So, and if you look more qualitatively at what they do, you see, for example, here that the space of action words is nicely divided into subcategories in the experiential grounded model, but the distributional model makes a big mess here. So it's not really well able to separate different types of action words. Likewise, here in the object word space, we see here in the distributional model a very nice delineation of this category. This is food words in this case, and while here in the experiential grounding model, we do not see much. It seems that this category, this subgroup, is subdivided in different parts. But on the other hand, here we see a very good mapping of this category of animal words, which is not so clear in the distributional model. So essentially, we see semantic similarities of different kinds, best captured by the different models. There has been recent research on brain activation, where people then looked here, for example, a study by Fernandino, where they looked whether the brain activations patterns would actually be similar to the semantic similarity structure of different semantic models. And their message in the 2022 paper was in PNAS, they said grounded models did much better than competing semantic models. Here, for example, in red distributional models. So they say, if we look at the brain, if we restrict consideration on those areas here in red, which are thought to be semantic hubs, then we see that the similarity of brain activation, the similarity structure of brain activations is best matched by the similarity structure of the grounding of the grounded semantic vectors. And this is so we took a slightly different approach. We did not restrict our consideration. Francesca Carota and in collaboration with Nico Kriegerskort's group, we did a series of studies of a similar sort already much earlier. And then also here in this study, we compared directly an experiential grounded model with a distributional model and found here entirely distinct brain areas that mapped these semantic similarity. So unlike the previous study by Fernandino, we see just dissociated brain areas that map the different types of semantic similarity. So from here, the suggestion arises, adding grounded semantic information to distributional semantics may lead to a more complete picture of the semantic space. So we would then include, of course, symbol referent relationships, word learning, and likewise, and those would likewise go into representational semantic similarities. And yeah, so this is one of the suggestions I would make. The other vaguer suggestion or more tentative, sorry, not vague, but more tentative suggestion is that if we build networks now not according to the most efficient method at the moment, but if we allow the networks to become more similar to the brain and biologically realistic, we may observe, and we did this in a series of simulations experiments, that with realistic neural network structure and Hebbian learning, so a realistic type of learning, also not error back propagation or some other error-driven algorithm, and we see the development of categorical representations and indeed symbolic representations, in the sense that we see then in the network representations of a word form interlinked with neurons that symbolize or index, are grounded in different semantic features of the reference of the category term. And so the individual neural elements may correspond to a feature like has 4 legs or barks, here in the case of the word dog and the different dog exemplars. And here it's entirely clear that if we activate the word form representation, we get activation of these semantic feature neurons in the conceptual part of the grounded representation. But the other way round, the activation does not work if we only activate this single neuron, and its few connections to the word form representations will not be sufficient, simply because more activation is necessary to activate the linguistic semantic representation. So far, my comments. I thank you very much, and thanks again for an excellent talk.
And thank you for an excellent commentary.
Yeah, yes, if I can add, okay. Well, I think I kind of agree with you in the sense that there is some of the results that you showed are in line with the positions I had, in the sense that if you go to the slide about the distributional space, right, the difference between the distributional, the similarity, and that one, exactly. So it's interesting how the distributional model, pure distributional information, has a much more messy organization than pure experiential one, right? And this is concerned only semantic similarities, where in a way, what I consider in the talk were different type of semantic relations that are already, I think, even more complex than semantic similarity. So I think this exactly is consistent with what I claim, in the sense that of course, there is an overlap between what is encoded in language about the word and the word itself. Okay, there is an overlap so that we can recover a lot of semantic information from distributional data alone. But this type of overlap is not a perfect isomorphism. It's not a perfect alignment, so to speak. That's why, in a way, I mean, we cannot simply take distributional data as a surrogate for experiential one. I totally agree that, for instance, adding also, that's why this is also what I mentioned in my last slide. So for instance, why not imagine that these models actually learn basic semantic relations from the grounded world, in the sense, I guess that, basic cognitive relations like part of or location or spatial relations are truly acquired not by a language, but are acquired especially from grounded experience.
Yes.
So,
Yeah. And indeed, it's so. If you look in the literature, in the philosophical literature, in the psychological literature, it's indeed so that, for example, Hume claimed that from experiencing billiard balls, you can learn the concept of causality.
Exactly.
And then one step further, it was um, uh, it was Piaget who actually said that that the child learns the concept of causality now not with billiard balls, but rather with making an action and observing the consequence.
Exactly. So basically, even for causation, so to speak. So the problem is that, of course, these models learn this type of relations only by and through linguistic patterns. The problem is that these linguistic patterns do not, let's say, isomorphically correlate with causal relations. So because, for instance, we express causal relations in languages not always in the same, we don't describe in language cause and effects in always in the same way in which experience them. Okay, and that's why I think that's also I think it's where lies the problem. So the fact that these models only acquire semantic relations through language. And so I think that one way, of course, one possibility, that's why it's something that I skipped in a slide. I said, okay, some people say, okay, let's assume that you could interface this model with some symbolic knowledge base. Okay, but I don't think this is the correct answer, because we need to make models that are able to learn this type of relation and to structure this type of conceptual theory from data. The problem is that these type of theories are probably learned from the wrong type of data, and so on, because for instance, even the so-called multimodal language models like GPT-4, GPT, and so on, do not learn some relation from scratch image data, from multimodal data. They simply combine let's say, a huge model learned from language, from a huge model learned from data, from image data. I think that, for instance, it would probably a viable possibility would be to explore whether basic semantic relations could be learned first from non-linguistic data, and then use this information as a kind of semantic constraints for the model, then to apply this type of relations to other data and so on.
Yeah, this is a very important point. And it could be that the two strategies would be complementary. And this is also what this slide, by the way, suggests, because here we have an integrated model where the semantic similarity spaces are, so to speak, summed up. And here you see a very nice delineation of all the subcategories. So taking the best of both worlds.
Exactly. So I think my position is, of course, that distributional data allow you to project grounded knowledge also to other things that you have not directed experience, right? But in a way, you need to have some grounded information from started with in order to learn basic, let's say, the basic component of the conceptual theories. And those basic components like causal relations, part of, location, and so on, I think are not directly to be learned from linguistic structures. That's the idea.
Yeah, sure. I think we fully agree there.
Okay, we have some questions. Do you want to continue, or there are some questions from?
No. Please.
Okay, Julia, but keep the questions short and the answers short. We have very little time left.
Yes.
Julia Zimmerman and then Nicolas Goulet.
Hi, thanks for the talk. I was wondering, when you interpreted the part of feature from Templeton, why not interpret it as meronymy plus a metaphorical extension of meronymy?
That's a possibility. The problem, yeah, absolutely. But that's exactly the point in the sense that, in a way, a meronymic extensions is not the same one as a true meronymy relation. That's what I meant. Okay. I think this type of information, it's really something which is encoded in a linguistic pattern. The linguistic pattern exactly encodes the true meronymy plus a lot of extensions of it in a non-true meronymic interpretation. So, of course, my point in showing that the small example is the fact that we should be, I mean, we still have to understand how this type of basic and semantic relations are truly encoded by these models. These alleged semantic feature of the models may still be a lot of connected to surface linguistic patterns rather than truly semantic elements. That was my point.
Okay. Nicolas,
Yep.
short question.
Yep. I was wondering if you think that semantic formalisms like abstract meaning representation or the more recent one, BabelNet meaning representation, are of interest in the context of bridging the gap caused by the missing link you described?
You mean the abstract meaning representation?
Yep. For example, because it seemed very similar to the graph you showed on your last slide with the...
Yes or no, in the sense. Okay, yeah. The point is, that's what okay. I think that the problem is I would like the model to learn this. I mean, we might try to learn this type of representation from annotated data, for instance, in which you have this explicit relation. It would be like saying, okay, I have some. I learned this type of relations from pairs that I know from that are meronyms or encode some other type of relations. Okay, in that sense, I think that might be a useful try and a useful experiment to do. What I wouldn't like to do is to have a kind of neurosymbolic approach in which we have let's say, the language models and, for instance, a formal language on which you want to map, on which you want to translate your linguistic expressions. For instance, like in the probabilistic language of thought hypothesis, which, I mean, I think it's a really fine model, but it's assumed that you basically took the language models and the language model translate natural language into these formal structures that are then given an input to a formal engine. So I think that in this case, it uses this type of combination of language model and symbolic representation. I don't find it very interesting for me, at least in the sense of asking the question, how do we learn this type of knowledge? How do we learn this type of structure in that sense?
Perfect, thank you.
Okay, I'll end this session now and remind you that the next speaker will be Danilo Bzdok and not Tom Griffiths, who has been moved to Friday at 3:30 p.m. because of COVID. Thank you both very much.
Thank you.
Thank you.
Thank you, Friedemann, for your very nice discussion.
Yeah, thank you for your excellent talk and for yeah for the nice interaction. See you.